All right. Why don't we get started? So where we last? Oh yes. So homework is due on the 30th of January, which is today's the 20th, Thursday, at the usual 1 second before midnight. Okay. And if there are glitches with Blackboard, which sometimes there are, please just send me preferably via Slack with direct message, not to the channel for the class. Send me some proof of your attempt, and I will act accordingly. Okay, but also don't wait till the last minute either. Okay. All right, so where we last left off, we talked about this idea of layering, protocol layers. And this is a software engineering construct to manage the complexity that is all of the different pieces and the associated software services associated with all the many components that collectively comprise a network. And as we talked about last time, what you are very deeply concerned about with a network is the so-called end-to-end flow, right? Because at the end of the day, it doesn't matter as much what's happening on a link or across a packet switch and so forth. What people remember is the perceived experience of the bits at the particular endpoints. And an example that I've been carrying forward is, say, if you pull up your browser, you go to Netflix.com, and you start to view a movie. Of course, if some link along the way is experiencing slowness, maybe there's a router that's experiencing congestion, the untrained user, not all of you sophisticated folks, the untrained user will blame Netflix. Oh, Netflix stinks, right? When in fact it's really just congestion at a router along the end-to-end path between the server instance at Netflix's data center. It's one of the many data centers they have across the country and around the world. There's some issue with a component along and between the endpoints rather, along the way from their server instance to your browser. And so we have a lot of pieces, and we talked about those pieces: applications, protocols, routers, hosts, and so forth. And of course, when you have all these moving parts, for it all to work well, you have to have some good software engineering principles, and that principle employed for the network or for the internet is layering. And so layering affords you two things. It makes it easier to understand, so you can have separation among certain types of functionality or functions. And it also allows you to very easily replace components so that you can change the behavior without doing too much damage to the entire system. So continuing along, the example carried in the book concerns air travel. And in air travel, if you think about it, there are a bunch of different steps to traveling by plane. And each of these steps has a certain purpose and with its peer across this diagram, and each of these steps makes use of services or facilities or functions of the step either below it or above it. So directing your attention to the top left of this figure, we have the ticketing process. And so, you purchase your ticket. I remember when I was a little kid, probably like 3 years old, you drive to the airport. That was when you could park in front of the airport, right? Get out and go inside. But it's certainly different from what happens today. But nonetheless, you'd have to go drive to the airport or go to a travel agent and you'd buy a ticket. And so that ticket's purpose is certainly to identify that unit of travel that you will be using for that particular journey scheduled by the airlines. And so that ticket interfaces with the baggage check. You show up for your travel and you go to the counter and you check in your baggage, and that associates your baggage with that particular unit of travel that you will be using, you have purchased, so you're allowed to use it, and it's for your exclusive use, unless they oversell it, but that's a whole other question. All right, so then once you get that baggage, you get a baggage claim check. Now, of course, this is theoretical because no one ever really checks the baggage ticket, but in some airports and some locations, depending on circumstances, they're not going to let you leave baggage claim with a bag unless your baggage ticket matches what's the tag that's on the luggage. But nonetheless, the baggage claim check has meaning, and that's after you check in your baggage, and that identifies the linkage between you and that piece of baggage that's traveling in the belly of the plane. And so then from that baggage check, you go to the gate, and the gate is where the passengers on the plane queue up and prepare to fill that airplane before it's off on its journey. And then, of course, once the plane is loaded, of course, they get cleared for takeoff and they make their way onto the runway. I'm not an aviation person, so I'm more of just a casual user of this. So that's all I'll say about this part. But nonetheless, once you leave the gate, you get to the runway where you take off, and then you have airplane routing that happens. And as I understand it, you are handed off, you being the aircraft, is handed off from one routing tower to another. And not only do they have routing towers at the air traffic control center at the airport, but there are all sorts of routing stations dotted throughout the country, and you're given what's called a vector, which is a magnitude, your speed, and a direction, and you literally hand it off from one route to another, and you stitch together these vectors, and you have your journey that you traverse throughout your flight. So then that last step on the routing, you're handed off to the tower, which then understands the status of each of the runways. And then when a runway is clear for your vessel, for your aircraft, clears you for landing at a particular runway. And so then after your landing, you taxi up to a gate. And then, of course, the reverse of the baggage check, you have the baggage claim where you pick up your baggage. And then, of course, if there was something favorable or unfavorable about your journey, you can file a complaint. Maybe they lost your luggage, maybe you didn't like the flight or what have you. And so at each step along the way, each layer, there's a piece of information that's meaningful to that particular aspect of this system. You have this idea of travel by airplane, and its travel by airplane consists of a bunch of components. Those you can think of as layers, literally, that cuts across. You have the ticketing layer, and that ticketing layer identifies that particular unit of flight. And that ticket number or flight number stamped onto the ticket is how you identify that particular unit of travel should you have a complaint that you'd like to register or you'd like to file. So then you have the baggage check. Now that baggage check has a claim check, and there's some information printed on that, and certainly it matches the tag that's on your luggage applied when you do the baggage check. Now, this baggage check information is meaningful to the other baggage layer on the receiver side when you are at your destination airport. And so on the receiver side, this information, it's meaningful in that it identifies the particular piece of luggage that you had given to the airlines when you did the baggage check process. And so the gates, you also have the loading and the unloading. And the main point about this analogy is that you have a series of steps. And at each step, you can consider it as a particular type of function. It has to do with baggage, or it has to do with loading, getting people onto or off of the plane, and so forth. And for each of these layers, you have a piece of information that is uniquely meaningful to each one of these layers. And so for that particular layer on the left-hand side relating to departure is information that is meaningful to the peer layer, if you will, the same layer on the arrival side, and it's only meaningful to that layer. The additional part that's important to observe here is that each layer implements a type of service. It's a type of function. It does something. And so when you get your ticket, getting this ticket and you purchase, you exchange money for this ticket, you're reserving or setting aside a unit of travel for your exclusive use. And so not only does it identify you, it kind of tags you or links you, if you will, as the owner of this particular unit of travel for that particular scheduled journey on the aircraft. And so each layer also implements a service. It does something, has some behavior within the system, and it also interfaces with other layers. And so these interfaces can be with the layer adjacent to you, below you, just below you, or the layer just above you. So for example, your ticket purchase makes use of the baggage check because, of course, if you want to check in some baggage, you have to identify the unit of travel that you'll be using because you don't want your bag to go someplace else, right? So you're associating your bag with that unit of travel, and therefore this baggage ticketing, ticketing layer is going to make use of the services below for the baggage. It says, all right, well, this is a unit of travel. I want to say, this is my unit. I'm going to pass you some information so that you can then add some other information to it, associate this bag with this unit of travel. And so the baggage check also uses the layer below, which is the gate function, right? Once you've done the baggage check, you've associated the unit of travel with a person at the ticketing, the bag with it, and now you need to know where that plane is so that you can actually physically use this unit of travel. And so those layers on the departure side, each layer uses information or passes information to the layer below, and you can think of the layer below as providing some service for use by the layer above. Okay, now on the arrival side, each of these layers uses or sends information to the layer just above, right? And as such, you can think of these layers as making use of services of the other layer that's just above. And so not only do we have this layering that is a good software engineering practice, it makes the system understandable. Also, it affords you the ability to easily change your scheme. So for example, you might want to change the way that you load the plane at the gates. So maybe you want to, call people up in groups like a lot of airlines do. Or maybe you do something like Southwest, where you say, okay, you can go ahead, this group of people, you can pick your own seat. And so you can totally change the way you do the loading at the gate, or you could totally change the way you claim baggage, and this diagram doesn't change. You don't disturb all of the other features or services within this complex process if you have this layer. It's a nice, elegant, and compact way to do what's called separation of concerns. So they also use layers above and below, and they pass information to one another, and these pieces of information is meaningful for a particular layer. Okay. Any questions about this? Does that make sense? All right, so we're going to relate this to networking. And so layering is a good thing in general, and it allows you to identify also relationships between the pieces that collectively comprise your complex system. It makes it easier to maintain things because you could update the baggage check process, and that's not going to disturb what happens when you're loading things at the gate. And so layering can certainly sometimes be harmful because when you do layering, you're adding extra complexity. And when you add that complexity, sometimes that introduces a degradation in performance of the system. Okay, so this is a description of the modern Internet protocol stack. It's 5 layers, and this is how we think of the services, just like we talked about air travel. This is how we think of the services in the modern Internet stack. It has 5 layers, and going from top to bottom, since it's a top-down approach, it's application layer, transport layer, network layer, link layer, and the so-called physical layer. Now, certainly, maybe if you've done a Cisco course or some other networking, you learned something called the 7-layer ISO model, and that's largely defunct these days because, and I'll explain in the next slide why it's defunct. But nonetheless, when we talk about the physical layer, that refers to the actual encoding the signal information for the bits on the wire. And so the physical layer, if you're dealing with fiber optic strand, would represent all of the machinery that you need physically, circuits and stuff like that, to send pulses of laser light at certain frequencies through those strands of glass, in addition to the repeaters that amplify that signal to push it another 50 miles at a time. So then this physical layer deals with bits on the wire. And then we have also on top of that the link layer. Now the link layer is responsible for transferring data between neighboring or adjacent components. When we saw the diagram generally about the network, we had packet switches, and we said neighboring packet switches are connected by some physical link. Right? Now that link could be wireless, or it could be wired like coaxial cable, twisted pair copper wire, or fiber optic strand. Now the link layer's job is to deal with all of the services, all of the issues concerned with transferring data across a link between 2 neighboring components. On top of the link layer, we have the so-called network layer. Now, the network layer takes a step higher level consideration. It's associated with a special piece of information called an IP, or an Internet Protocol address. And what this network layer is responsible for, not just single hop sending of information, it's responsible for the more global consideration of sets of hops that information will travel when getting from some source to some destination endpoint. And if you think about sources and destinations that are separated by more than one link, more than one hop, you need some other pieces of information. You need first an identifier to identify that endpoint where that message will originate or where that message it will have as a destination, but you also need to determine over which links this message should pass. And that's where the so-called routing protocol comes in, right? So this IP address is meaningful to the network layer. It identifies the network interface globally on the network, and it also has a routing protocol. We did mention at a high level the so-called forwarding table portion of a router or a packet switch, and we also talked about the routing algorithm, and we'll get into that in great detail when we get to the section on the network layer. And so the network layer is responsible for aggregate routing across multiple hops of data between a source and a destination endpoint. On top of the network layer, we have the transport layer. And the transport layer is responsible for so-called process-to-process communication. A process is nothing more than a program in its executable state. And when you think about what happens when you pull up your browser and you type in, say, www.disney.com and hit enter, well, the process or program running your browser is now talking to the process or program and or program and execution running in the data center for Disney, right? And so while the network layer can get your data to a particular machine, to a particular network card more correctly, once you get to a machine, you get data to a machine, you have to decide from which application it comes or to which application it's going to go. Now, certainly, let's say you're running Dropbox or, you're running Skype and you're also running your browser. Now, once that packet gets to your machine, right? Something has to decide, is that packet going to be delivered to your Skype and you see the video conference, or is it going to be delivered to your browser and you see the Disney movie, for example? Likewise, on the outbound side, when you send data out your machine, it can come from different places. It can come from your camera if you're using something like Skype for video conference. It could also come from your browser. Maybe you're trying to slow down or change the resolution of your video stream from Disney.com. And so this transport layer then needs to identify the process. And this is where we'll start talking about the port number, and I'll get into that in great detail. But if you're dealing with sending data to the application itself, process-to-process communication, you need to consider what the needs are of that application as it pertains to the data in which you are trafficking. So some applications, they need that data to be delivered or sent reliably. And reliably can mean multiple things. It could mean the data is not corrupted. That's really important for applications like banking, right? If you have a binary 0111, that's 7. So maybe it says you're going to send $7. Now, if that gets corrupted and instead of 0111, it's now 1111, that's now $15, right? And so you can imagine you can't afford in any banking application to have those packets get corrupted, meaning that some of those 1 bits are changed to a 0, some of the 0 bits are changed to 1. So one of the things that the transport layer offers is 2 different types of services. The major flavors are called TCP, so-called Transmission Control Protocol, and UDP, so-called Unreliable Datagram Protocol. Now, TCP affords you reliable data transport. So that means the error checking, but it also means the order in which you send that data is also the order in which it's delivered to that endpoint on the other side. UDP has absolutely no guarantees, but the cost you pay for that reliability is a degradation in end-to-end throughput. So the price you pay for reliability is a slower send-receive rate. The price you pay for the benefit you get for that price you pay for unreliability for UDP is that it's much, much faster. So some of your considerations, if you're going to write a network application and your application is going to use some transport layer, you have to characterize what the data needs are for your application. Do you need reliable data or can you afford unreliable data? An example of unreliable data is audio streaming, right? If your audio has a corrupted bit, maybe it sounds a little off, you rewind it and restart, or you just ignore it, right? It's not catastrophic. But for something like banking or email, in an email, you can't afford for bits to get changed or corrupted because you end up with just like garbage on your screen when you're trying to read that email, okay? So lastly, we have the application layer. And the application layer supports the applications that you know of. The big one is HTTP, Hypertext Transport Protocol, which is what powers the browser infrastructure. Now, there are lots and lots of applications that so-called piggyback on top of HTTP. It's a perfectly good protocol. And so RESTful SOA, RESTful Software Oriented Architectures, they make use of HTTP gets in order to send messages that ultimately call functions on server processes. Okay. We also have other applications, application layer protocols, Simple Mail Transfer Protocol, SMTP, and FTP. FTP is not really used because it's not secure, but there's SFTP, Secure File Transfer Protocol, to transfer files back and forth. Okay, and so with the application layer, we have our protocols, and I'll describe a little bit more about protocols as being a scheme and a structure for data, and then the intended behaviors about what the endpoints will do when you see certain values in certain parts of your packet. Okay? All right, any questions about this? Does that make sense? So this is the modern 5-layer internet stack, and I remember way back when I was first learning this, we learned the ISO reference model, right? And it was 7 layers. And I remember the moniker we'd remember, P for physical, link for network. We'd say, please do not, well, link was called data link back then, but now they just call it network layer, link layer. We'd memorize, please do not throw sausage pizza away, right? P for physical, do was data link, not was network, throw was transport, throw sausage session, pizza presentation away application, right? And so I'm not going to belabor what each of these does, but I will say that the top 3 layers, application, presentation, and session, are now rolled into the application layer in the modern 5-layer stack because it was acknowledged that it's best to designate those top 3 layers as being functions in the application. Right? And the goal in doing that was that you want to keep that complexity out of the network core, meaning the switches and the routers, the packet switches. Because if you keep them as simple and as basic in their function as possible, you can make them really, really fast. And in fact, modern high-speed routers will have custom silicon, custom chips that will process a packet, not in software, but in hardware. Right? And you can do that when you keep things very simple. Okay. Any questions about this? Does that make sense? So please do not throw sausage pizza away. The sausage pizza away is now just away application layer. But I still remember it like it was, well, it wasn't yesterday. It was like probably like 20 years ago, but nonetheless, I still remember it. Okay. Make sense? Okay. So let's take a look at what happens. This idea of layering, I mentioned that each layer has information associated with it that it is meaningful. And so this idea of encapsulation refers to the fact that each layer is going to add its own piece of information that's meaningful. Now, certainly, you call these packets different names depending on who's dealing with that packet of information, right? So we start out in the application layer, top down, with what's called a message. An application layer message is all that information that's meaningful to that application. So your HTTP GET message, which you've seen in Wireshark, that's meaningful only to your browser and to your server. Right? It doesn't mean anything to any of the other layers and components in the 5-layer stack. So then we come down and the application sends that message into the transport layer. And the transport layer says, aha, this came from the browser. Oh, that came from Skype. And it adds its own piece of information, this identifier, which we'll learn is the port number, that uniquely identifies every single application. And this is what the transport layer uses in order to know from whom did this packet come from and to whom on the inbound side does this packet get delivered. So we take that message and we encapsulate it, meaning everything that came from the application layer, when it is sent into the transport layer, it gets wrapped or encapsulated, and then the transport layer adds its own piece of information, something called the transport layer header. And so H sub T just schematically here represents the transport layer header, and that's all the information that the transport layer needs in order to send to another transport layer across the network. It's meaningful only to transport layers. Now, when you take this encapsulated message from the application and you wrap it up and add a transport layer header, now your packet has a different name. It's now called a segment, right? So when you say a message, it's application layer. When you say a segment, it's the transport layer unit of data that is trafficked across the network. Okay. Any questions about this? Make sense? So continuing on with this idea of encapsulation, the transport layer, once it identifies the application that originated the data or that will receive this segment worth of information, it then passes it down on the outbound side to the network layer. And so now the network layer, it wraps up all this information from the transport layer, which still includes the message from the application layer, and it adds its own piece of information, namely the network layer header. Now, when you have this form of packet, it's called a datagram, right? So network layers traffic in datagrams. It is the segment from the transport layer wrapped up, and the network layer adds information to it consisting of the internet protocol address and other bits of information we'll certainly talk about in great detail. So the network layer then takes the datagram and it sends it down into the link layer. The link layer adds its information to this network layer datagram. It adds the link layer header, and this is information that the link layer needs to identify other link layers on the network. Now, one of the important pieces of information that the link layer needs and understands is called the MAC address, the media access control address. And that's that funky number in hexadecimal that you see if you were to look at your networking information associated with your network card. And that's how your machine is able to contact other machines in the area. If you're ever take the opportunity to go through the network settings, sometimes your interface will allow you to set your network card into two different modes, one called infrastructure mode and one called ad hoc mode or peer mode. Now, when you're in ad hoc or peer mode, you can now send information back and forth only to network cards that are locally in your existing network in the broadcast radius for the antennas wirelessly in your laptops. When you're in infrastructure mode, it talks to the local switch or router that's closest to you, your gateway, and when you're in infrastructure mode, it will then contact that gateway, deliver packets to it, and it can because it's on the same network, and that thing will now send it off your network someplace else. Okay? All right. Any questions about this? No? All right. So then, of course, you have the physical layer, and that's where transmission comes in, right? And so here, when the link layer talks to the physical layer, that's typically involves some interface between hardware, software, and physical medium, and that's where you get the encoding of those 0 bits and 1 bits into signal information, be that frequencies of electricity, electrical signals, or pulses of light, laser light at different frequencies. Okay, so this is called a frame when we talk about the unit of data. It is the link network layer datagram that has been enveloped, and added to it is link layer header information that's meaningful to all the link layers. And so once you transmit it through the physical, of course, it makes its way bit by bit to the other components. And we won't talk too much about the switch, but a switch is a so-called layer 2 device because it deals with things in layer 2, which is the link layer. And when you number these layers, often you talk about a packet switch as a so-called layer 3 device because it deals with layer 1, 2, and 3, physical, link, and network. And so this message, this frame rather, gets transmitted and it goes to a component. And when it arrives at a component, in this particular example, I'll depict the arrival at a router or packet switch, as I've been calling it up to this point. And it arrives through the physical layer, so that's where the signal information gets collected, put in a buffer, and then that frame is delivered to the link layer. Now, the link layer gets this frame in the router, and you notice here it's going up these layers. When it arrives at the link layer in the router, first thing it does, its link layer examines the header information for the link layer, right? And so it takes this header information, processes it, and does the right actions that are prescribed by the protocol in response to what the value of that link layer header is. So it strips off that link layer header, and the resulting unit of data is a datagram. it sends it up to the network layer, right, after it strips off the header and takes its actions. And the network layer now sees the network layer header, and that's meaningful to the network layer. So this network layer then takes that network layer header, including the IP address, and it does some processing, and the result of that processing is a so-called forwarding decision, the sending of this datagram out some outgoing link. So the link layer does that, and it recalculates some stuff that we'll talk about in great detail, and then it sends it back down the hierarchy on the outbound side. So when it sends it back down the hierarchy, it recomputes a different network layer header and sends that datagram into the link layer. That link layer recomputes a link layer header. So now it's a frame, and it sends that frame out over the network. So that frame gets encoded in the physical layer of the router, and it makes its way the signal energy along this link, and then that same process happens when it ultimately gets to the destination. And so at the destination, of course, it hits the link layer. It takes some action based on the link layer header, strips it off, sends it the resulting datagram up above to the network layer. Network layer does similarly with the network layer header, strips it off, takes some appropriate action, sends it up to the transport layer. Transport layer sees the transport layer header, including the port number. It knows which application to deliver the message payload to. It delivers it, and now you see your video, or you hear your audio, or you see the email, and so forth. Okay. Any questions about this? That makes sense? So you might think, oh my gosh, that is a mess. It's not a mess. It's a bunch of behaviors, if you will, or services. And it's really important that the interface that encodes what these layers do remain fixed and well understood, and they just work together. Now, of course, as a computing professional, it's a really good idea to understand at a gross level what these things do. But the focus of this course is in understanding the engineering decisions about the choices you can make for these different layers and what the resulting capabilities are and performance is of the resulting collection of decisions for each of these layers. Okay, does that make sense? Okay, any questions about this? All right, so this is encapsulation. And we're going to finish up the module, 1233, with a discussion about network security. And then if we have time, hopefully we do, we can just jump into the beginning parts of the application layer. And so, of course, a lot of people are interested in cybersecurity. And one of the problems with the modern internet is that in the beginning, it wasn't really intended to be secure. And so certainly people have done a great job retrofitting the internet stack with security mechanisms. But in the modern age, when you design a network application, you must design it with security in mind deliberately. And so the field of network security talks about how malicious operators can attack networks. And you might wonder, well, why should I care? Well, you absolutely should care, particularly as more and more of the human experience makes its way online. And you're going to see a lot happen very dramatically 5 years from now, only 5 years. It's going to be a very different world 5 years from now from today, right? When 5G gets rolled out, and it's more commonplace, you're going to see something like 5 gigabit to 10 gigabit per second speeds wirelessly, right? And so what does that mean? With every disjoint leap in technology, you have a lot more applications that are enabled, right? Now, I remember, when I was your age, there wasn't a real internet. There was something called Gopher, but I had the privilege of seeing the World Wide Web develop. And I remember when you had speeds that were like 48 kilobit per second, you could have static web pages. And then when those speeds jumped up to megabits, you now started to see animated web pages. And you could do things like send graphic animated GIFs, right? That was how people did it. So then after that, you got additional speed improvements, and now you saw video and music and stuff like that. And more stuff went online as the speed caught up to accommodate that. So now imagine what you do wirelessly. If you had 10 times the bandwidth, what could you do in the future? And so one of the big developments is the ability to purchase things. So have you ever gone to the airport to purchase a ticket? No one? No one? No, you shouldn't, right? You all go online, right? Now, I remember when you purchased a ticket, it wasn't that long ago, right? You'd have to go to a travel agency or you'd have to go to the airport yourself. Now it's unheard of to do that, right? So that has certainly changed. Anyone kind of tinker or dabble in like trading stocks? No, trading stocks a little bit. So you go on, open a TD, not to plug anyone. If you're listening, TD Ameritrade, how about a sponsorship? No, but because it goes gets posted. But you could go to a popular investment house. I won't mention any particular brand until they sponsor me, but sponsor you. But you could open up a TD Ameritrade account or some such thing, a Schwab or whatever, and then all of a sudden, electronically, you don't even have to go in person, right? You can electronically set up the account, link it to a checking account, transfer money, and all of a sudden start buying and selling stock. Right? You can now go to the finance.yahoo.com or some other such thing. You can check on the stocks. You can see the Reuters press releases, and you can make your own decision. Just decide to go and buy and sell stock. Now, not that long ago, you'd have to call up a broker. You have to go into the office, set it up. You'd have to phone call the broker. This call is being recorded for their own, covering themselves. And you'd have to tell this person what you wanted. They'd submit the order, give you a confirmation number. You'd write it down. Then you have to go and check on this confirmation number, make sure it happened. And then you get a statement in the mail, right? That's all instant now. And that all happened because you had these increases in bandwidth. So as more and more and more and more stuff makes its way online, it's going to be even more important for network security. Mobile payments, that's one thing that's coming online. Now, of course, some people use PayPal, some people use Apple Pay, but at some point it's going to be weird to carry cash. Right now, a lot of you, and let me ask, who actually uses cash to pay for stuff every once in a while? Now, sometimes if I go to a store that, kind of looks a little shady, I don't know what they're going to do with my credit card, I'll just use cash, right? But for the most part, a lot of people use cash. Now imagine, let me ask you this. Does anyone have virus protection for the cell phone, for the smartphone? Just three of us, right? You're going to have to at some point. Now imagine if someone hacks into your cell phone, right? Now they have access to all your mobile payments, right? And they don't even need to do that silly thumb thing or the face recognition stuff. Get into your phone, they have your address, they have your transactions, they have access to all your pay systems. A lot of these apps, you pre-sign on, right? So now, just by accessing your cell phone, they can check your account, initiate transfers, and do all sorts of wonderful things, right? Without you even knowing. You just sit there, someone's on your phone. So this idea of security, especially when we go to mobile, is going to be very, 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 very important, right? Imagine someone hacks into your car, right? You have 5G on your car, tracking your location. Someone knows roughly when you're at work, right? Someone knows when you go on vacation, all sorts of stuff. So it's really important in the future, especially as we go to 5G, to make sure that when you design an application, you have security in mind. Now, of course, you've probably now heard about all these data breaches from TJX companies, Target data breach, Facebook data breach, all sorts of stuff, right? It's going to be really, really important. And so in network security, we talk about how to defend networks against attacks. Now, there are attacks where people exfiltrate or steal or take information and use it for some purpose. There are other types of attacks where people try to deprive you from something. So take, for example, Amazon.com. Right? Amazon makes billions and billions of dollars. So having their website accessible relates to money, right? Millions of dollars a second. Now, if someone were able to prevent people from accessing Amazon.com through some means, well, what are you doing? You're depriving Amazon from making a living. There was one, I forgot the name of the exploit. I think it was the, what was it called? Where they locked down data and extorted you to pay ransom to unlock the data. I forgot the name of the exploit, but there was an exploit. The name escapes me right now, where you send out a bunch of illegitimate emails. You only need one person in an organization to click on it, and then it proceeds to go and find all your data stores and encrypts your data. Phishing as an approach, and I'll get to that, and it's very good. It encrypts all your data and then pops up a message that says you need to send so many units of Bitcoin to this Bitcoin address or it will never be decrypted, right? Now, entire cities have been brought to their knees in law offices through this exploit. So it's really, really important, A, that you don't click on emails if you can't verify who it's from and the circumstance in which it's sent. But there are other ways of launching attacks, and one way is to also deny people of usage of some resource, be that data or server or what access or what have you. Um, and it all comes from the fact that the internet wasn't originally designed to, which is kind of odd because the internet started as an Army research projects exercise, right? So you'd think if it was originally created by Army and the Defense Army Projects Research Agency, that they would have security in mind from the beginning, but that wasn't how it developed. Okay, so there's something called malware, like software, malware. Mal from the Latin means bad software, malware, right? And malware can is the mechanism that people use to gain entry into a system. Now, one of the ways people gain entry through malware is virus. Now, virus is particularly interesting because modern viruses are self-replicating. And these things might look like emails that seem legitimate. You click on something. And there's one interesting exploit that I actually have personal experience with, not as a victim, but as research, and I'll talk about that in a little bit, where just by clicking on a PDF with a popular, say this way, popular PDF reader program, you could take over someone's machine to do exfiltration. And so the interesting part about these, they're self-replicating, but they use your address book to do that. And that's particularly clever if you think about it, because if you get an email from some some unknown address, you're probably going to say, I don't trust this. I'm not going to pay attention to it. But if you get an email from someone that you get email from all the time, you're probably going to open it and you're probably going to give it some credibility, right? And so by infecting your system, not only does it run an exploit, but it propagates itself very quickly by looking at things like email logs and your email address book and sending itself to other people from your email address, making it look like it's from you. Because people are more likely to open an email that is from somebody they're more familiar with or somebody's address that they're more familiar with. Okay? So if I ever get a weird email from someone, I first think about, well, how does this person usually write an email? Right? Secondly, what's the context? If it's something out of the blue that I know nothing of, I do what's called an out-of-band contact, and they call the person up or text message the person and say, hey, did you send this thing about this thing? Even my own mother, right? My own mother sent me it was an email, it was a text message. This is like a week ago. And she had gone on a trip to Alaska. She's retired, now doing the things she always wanted to do. Alaska in the spring is quite nice. She didn't take us, but, all right, I'm grown now. But nonetheless, I had to teach too. But so she went to Alaska and to Denali National Park because she wanted to see those animals in person up close. It was wonderful. And so she was out of cell phone contact for quite a while. So last week, I get this text message, and it talks about Denali, Alaska. I'm like, yeah, that sounds legitimate, but that was like a couple of weeks ago. That was a long time ago. All right. So I called her up and said, hey, did you send me this email? Oh, yeah. My phone was out of reach. And then I finally turned on my cell phone. My mother, God bless her, she uses cell phones. She turns it on when she's using it and turns it off when she's not using it. That's what she does. And still, my brother and I are trying to work on getting her to keep it on so we can respond back. But so she used it in Alaska to send a text message, and it went out of service because they were in some remote area. And then she turned it back off again. And then the next time she turned it on was like literally months later, a couple weeks later. And then she finally turned it on, and the message sent. I got it. So, but nonetheless, that's just to say, if you get something that's out of context, don't believe it, right? Even if it's from someone that you know. But nonetheless, we have viruses, and they're particularly damning because they self-replicate, and the people who write them are clever in that they replicate using your address book for people that you already know. Then there's a worm. A worm provides infection by passively infecting you through something you might download, right? So you ever want to download like a Java development kit, a JDK, and you don't go, you just do a Google search, you don't go to oracle or sun.oracle.com or the official website, you might see this other website. Hey, download it here, right? Don't do that, right? If you ever download something and you're provided a hash, you probably want to use that hash and check against it, because what worms do, I can provide you some quote unquote really nice, useful software. And, maybe you don't want to incur the full cost, I'll say it that way, of a piece of software, and you find it very reasonably priced someplace else, and somebody has taken that software and packaged it up, they might have packaged in with that software other software that they can then use after the fact to recruit your machine to do something, right? So that's what a worm is. A worm is the piggybacking of malicious controllable behavior, kind of like a robot. You can get it to do something remotely, but it is embedded in some legitimate software. So that's just to say, be careful what you're downloading and what you're installing on your machine because it could have a worm inside of it. Okay? All right, any questions about this? Make sense? Okay. So spyware is another interesting type of malware. And spyware is kind of a really, really wonderfully insidious type of malware. It can do things like record your keystrokes. All it needs is to inject itself onto your machine. Now, I've actually seen in a network operations center range exercise spyware in action. And so imagine, you go to a website, it says allow cookies. How do you know it's allowing cookies? You hit allow, and then all of a sudden something is loaded into your machine, especially on Microsoft Windows, the C# object. And now that thing is recording your keystrokes. So it doesn't matter then what secure sites you go to for your banking. It's just reading your keystrokes and just phoning home and sending that information to some remote site. Okay? So it's really, really important. Be careful what you install. Another one is called a botnet attack, a so-called distributed denial of service attack. And this DDoS is one of those types of attacks where the malicious operators try to deprive you of access to some web-based or network-connected resource. And I'll talk a little bit about DDoS in a few slides. So this is an actual email that I got, and I've taken out some parts of it. I'm the graduate program director, and of course, you look up information on DSU's website, you call my voicemail, and you'll find out information about the deadlines for applying to the graduate program in computer science here. All the time, I get emails like, hey, click on this. I remember during the 2016 election, I have my websites and everything instrumented. We usually get about 350 hits a month on a rolling monthly average in terms of people going to the website. But during 2016 election, it went to like 2,000 or 3,000 a month. And if you traced where it came from, it was from Ukraine, Soviet Union, and from China, right, primarily. And there are the usual ones that it comes from for grad school, but not just to pick on those locales. And I remember there's this one where someone wanted me to click and download someone's CV to evaluate their experience. Now, of course, we only evaluate completed applications. I'm not going to evaluate something, but I also, that whole practice, trust but verify. And so I run webmail. I will never run Outlook natively. And the reason for running webmail is that it's downloaded to your machine and you can view the web page source code and actually see what the contents of this message is. And it was an exploit to try to pull information from my Dropbox account. Because, Dropbox, enough people use it that if you send out enough of these, you're going to get somebody's information, right? And so this is an actual email. So first of all, they misspelled my first name, and someone's in Angola, so we give people the benefit of the doubt. But then I checked the actual view web source on the tools view in the browser when you get stuff in webmail, and I actually saw the scripting code to try to suck information out of my Dropbox. Because, most people have the name of the folder is called Dropbox underneath your username. So question. It was something that looked like JavaScript and it had some other stuff, but it was a Node.js type PHP something or another script. That was a couple years ago, back in 2016. But people are clever, right? These exploits were coming during the graduate application season. So what happens during the graduate application season? You're gonna, kind of let your guard down a little bit and assume people are gonna contact you. Let's say you're a senior, right? I check your Facebook page and you say, oh, so excited, gonna be graduating, class of 2020. I look at DSU's academic calendar. Oh, this is when graduation is. I wait until maybe the week before graduation, and then I send you some emails. Congratulations on your graduation. Would you like to do blah, blah, blah? You say, yeah, that's great. Or I could send you something that looks like I'm the Alumni Association for DSU, right? All I need to do is to get you to click on something, and then I have you if I'm a malicious operator. And so a lot of people are very clever, and they will do things to try to get you to put down your guard long enough to get you to click. And that's all they need is a click. Okay. So this is a legitimate email, and I don't have all of it there. I remove some parts of it, but I get these all the time. And it always happens during graduation season because that's a great time when I'll let my guard down. Now, of course, running webmail is important because as a convenience, things like Outlook Express, they try to pre-run certain active components in your rich text mails, right? I like the browsers because it doesn't do that. And moreover, anytime you see an email, right, I assume I can't trust it. I look at the web source to make sure there's nothing insidious in there, and then make my judgment after that. Okay, so this is an actual email that was sent to me a couple years ago. And let's take a look at a denial of service attack. So in a DOS attack, you're trying to deny service. And as we said, you have these internet resources out there and people contact them. So Netflix's server instances in their data centers, they have to accept incoming requests to gain access to those movies with the authentication and all that stuff. And so one such attack, and I alluded to this when I showed you with a trace route that some routers don't like to respond. And I said that if you're identifiable, someone can attack you. Well, a DDoS attack is this type of attack. So what happens in a denial of service attack is that they try to suck up or use up all of the server capacity or all of the bandwidth, and in so doing, denying legitimate users access to that resource. So if I were to bombard or someone were to bombard Amazon's web servers enough, it would take a lot of them, but if you were to bombard Amazon's web server enough, then any legitimate person who wants to actually buy something, it would say, sorry, the server can't give out any more connections, and it would be depriving Amazon from the potential revenue for your purchase. So you make resources unavailable to legitimate traffic by overwhelming them with bogus traffic. So we have a bunch of machines, and you have a target server, right? And that's going to be the victim, this target. And you send out a bunch of emails, a bunch of malware, and all you want is people to click. Now, one of the issues with email, right? It's almost free. It costs nothing to send one. So all you need is a bunch of email lists, and on the dark web, it's not that expensive, not that I know. On the dark web, it's not that expensive to buy lots of email lists. In fact, you don't even need to be on the dark web, right? People post their emails all over the place all the time. So then you send that person illegitimate emails, and you could send out tens of millions of them. You only need 1% to get quite a few people to compromise. So you only need maybe one gullible person out of every 1,000, out of every 10,000 to be successful, because you can send out lots of these for very little cost. So now you break into some large number of hosts. Okay, and when you break in, what you're loading is some code that you can contact in the future, because just about everyone, or I shouldn't say everyone, many people are always connected for a large amount of the time. So then you say, okay, on Sunday at 12 noon, I'm going to activate all of them. So you have a list of all of those infections, because when they first infect the machine because the person clicked, the first thing it does is it sends a message and says, hey, I'm alive and I'm here. Right? So then after that, you coordinate them with a control program to at a particular time to now send bogus traffic to a particular targeted machine, be that a server at Amazon or what have you. So then you do that, and you all send at the same time, sending packets, and you overwhelm either the bandwidth or the machine's capacity to satisfy connections. Because machines have finite resources, eventually they run out of resources, and sometimes you'll find in your dealing with the internet, you contact a server and sometimes it says error, cannot connect, maximum connections. That's because that server has exhausted its resources. Or sometimes you have a very popular event and you ever go to the website and all of a sudden it's really doggedly slow because it's getting a lot of traffic and it's hard for that thing to keep up with the traffic. So this is a DDoS attack, and they're very effective. They're effective for two reasons. A, this idea of scale, but B, because this server has to accept incoming connections. That's how servers work. And so it can't tell necessarily if this is a legitimate connection or not a legitimate connection because it has to accept the connection in order to engage in this distributed application. Okay? Any questions about this? Make sense? Okay, so of course, there's lots of ransomware around there. There have been lots and lots of famous data breaches. One that's particularly very scary is the Equifax data breach. Now, Equifax is a credit score company. There are four of them: Equifax, TransUnion, Experian, and I always forget the last one. But there are four of them, and it's I think it starts with a V or something. Credit Karma is a company that subscribes to them, but there are four major companies that provide these credit ratings. And so these credit rating agencies, pardon? Experian, TransUnion, Equifax, and it's either L or V. I'll try to remember. I don't remember what it is. It came more recently, but nonetheless, Equifax had a big data breach, and if you think anyone would not have a data breach, it would be one of these credit rating agencies. The Government Accounting Agency a couple years ago, the GAO, had a data breach. No, I'm sorry, not GAO, the Office of Personnel Management, OPM. I misspoke. So there are lots and lots of examples of large-scale data breaches exposing people's information. And the so-called dark web, if you've ever heard the term, is this set of servers that aren't very well published, and people on these servers traffic in all sorts of illicit things. If you ever want to explore the dark web, you should probably use a virtual machine because you could end up infecting your machine with a virus. And you should probably use an anonymizing browser because you might be surveilled if you're browsing them. Because people often use the dark web for everything to all sorts of stuff. And so you want to tread lightly. But one of the things on the dark web is people buy and sell. There's like literally like an eBay for stolen information, credit card information, social security information, stuff like that. It happens. So you should really be careful about how you protect your information, and data breaches happen all the time, which is why personally I will never use my debit card for purchases. I use the credit card, not the debit card. Why? Because if somebody steals your debit card, they wipe your money out from your checking account, and now you have to sit there and spend a lot of time with the bank trying to get your money, right? With the credit card information, it's their money, and you just say, hey, this was a data breach. They write it off as a cost of doing business. And so I will never use my debit card to directly pay for stuff using a swipe. You can imagine things like gas stations right now. In fact, no, I'm not going to bring it up. Right now, you can buy equipment for card skimmers and for, these speed passes you have. You kind of go up and you, kind of just by walking by. You can buy a harvesting equipment for about $300 right now on eBay. And you put this antenna in a bag, maybe a backpack. You go to a big event like the Clifford Brown Jazz Festival or something in Philly, and you just walk around in the crowd with this thing, just collecting speed pass information, and they will never know. So if you have one of these broadcasting RFID types of credit cards, I suggest you get one of those little special metal card holders that electromagnetically shields the energy coming off these cards so people can't harvest it. Because imagine going to Philly, you're having a great time, and then a week or two later, you realize somebody bought like, $1,000 first class ticket, on your credit card. And now you're having to convince the credit card company that it really wasn't you, right? So literally you could go on eBay now. I'm not saying you should. And if you do, don't say Dr. Holmes told me to do it because I didn't tell you to do it. I'm just telling you about it, that people can steal your information quite easily. Okay. Any questions about this? So if you're scared, you should be. A healthy dose of that type of energy to get you more practiced in exercising good protective measures for your data is always a good thing. And if you have a Facebook account, you should always be looking at your security settings because new settings are introduced all the time. And unfortunately, their default for these new settings is often the most unrestrictive among all the choices, right? Okay, so data breaches. Packet sniffing is another, right? With packet sniffing, somebody sits there in promiscuous mode with something just like Wireshark. In fact, using Wireshark, you'd have to get a machine that allows you to do monitor mode, but you could set it up without, maybe in an afternoon or two. And they go out in some public area and they just start collecting packets, right? Now, what could you do if you can collect packets? Well, at some point, there's going to be somebody who's not going to exercise good protection. Maybe you're sitting at an airport in New York City or some major metro like Philly or whatever, and people are checking their stocks in the morning. You could figure out with enough traffic what stock is moving, what people are selling off a lot of, and so forth. Maybe someone's sending an email that's not as secure. You intercept that email. Maybe someone's looking up medical information just with a simple search query, right? You can figure a lot of stuff out in hubs like DC and New York and financial districts just by intercepting data regularly and analyzing that packet information. And so, of course, promiscuous mode is really important. If you have a public network, they often say, don't connect to a network if you don't know that network, right? Because somebody could be listening to your conversation, especially if it's not encrypted. But what you should do, if you're sending really sensitive stuff, you should use a VPN, a virtual private network. And maybe if time permits, I can talk about some of that technology. Okay, so that's packet sniffing, rather, and then there's so-called IP spoofing. Now, oftentimes when you connect to a server, in most modern, well-implemented servers, you'll see a so-called server certificate pop up, endpoint authentication. And so you'll see the little lock symbol on your browser. If you click on that lock, excuse me, it'll show you the certificate that authenticates that endpoint. Just because you connect to a server, it doesn't mean that you're on that server. If I snooped enough of your packets, maybe you go to WSFS Bank all the time in the morning in the campus center. So then what I do is I collect that data, and then I get there before you, and I put up a web server, and that web server, I intercept your request to WSFS, and then you connect to my machine, and then I connect to WSFS Bank on your behalf. So now every time you think you're sending stuff and getting responses from the bank, you're really getting it from me pretending to be the bank, but I'm forwarding your request to the bank and back, right? And in doing so, I record your information, and now I can do lots of stuff with that information. And so with IP spoofing, what you're doing is you're sending packets, but you're masquerading as some particular entity so that the user of that entity, that server, that resource, thinks that you're that resource when you're not. Okay? All right, any questions about this? And because people often reuse passwords, once you get one password, you try a bunch of different places. So if you're here in Delaware, either using WSFS, maybe using TD Ameritrade, Wells Fargo, it's not that hard to figure out 5 or 6 different banks that people here might be using. Okay? All right, any questions? No? All right. Let me do a time check. 1:04, okay, we have about 10 minutes. So this is some work I did in collaboration with my pre-DSU employer. I was a lead research scientist at Lockheed Martin, working on a bunch of things, machine learning in various domains, one of which was cybersecurity, but mostly sensors and kind of robotics-like things. And this is called AIR, Adaptive Immune Response. And this is in particular for exfiltration, so-called low and slow types of attacks. And if you think about what happens in a network, right, there's a lot of traffic going on. And what this low and slow attack does is it tries to steal information, small amounts of bits at a time, because amidst all the noise of all the other data swirling around that people generally don't notice. So let's say if you have a design for something, I could leak out that design, steal it over the course of maybe 1 or 2 weeks, and you would never even notice, a few kilobits at a time. And so this is based on some work called artificial immune systems. And if you think about what happens in virus protection, you have a signature for the bits of the malware, right? And when you run Norton Internet Scan, you say scan my system, what it's doing is taking this database of patterns of ones and zeros for certain known viruses, and it's checking all of your executables for these patterns of ones and zeros. So that's why when you update your virus signatures, you're actually downloading whatever the latest and greatest known viruses are. Well, that works to a degree, but a so-called zero-day attack, if you think about it, the advantage is really with the attacker, right? And so you have to get it right every single time, but the attacker only needs to be successful once, right, to do his or her job or intended purpose in stealing information. And so what I did, this artificial immune systems is a framework for how you do pattern recognition, patterns of ones and zeros, when those patterns of ones and zeros can change over time, right? And so if you think about what happens, someone writes a virus, and then they say, hey, let me add a feature, right? Just like you would with any software. You add a feature, and so now those patterns in ones and zeros are mostly the same, but it's changed a little bit. So how do you do virus detection for so-called zero-day attacks was the goal, where these signatures can evolve over time, because typically they're related, right? There's families and generations of virus signatures. And so we use techniques, and this is publicly available. You can download it. We use techniques from robotics, because in robotics, one of the things in what's called behavior-based robotics is you learn ways of behaving based on what you measure, right? And so the ways of behaving, the sequences of actions can change over time, and we have them change over time to match the changing virus signature. Now, state of the art at the time is you recognize a signature, and then you look something up in a table, and you execute what's encoded in that table. And here the goal was to adapt the behavior, the mitigating action. Okay, so there's lots and lots of opportunity in cybersecurity at the seams between other subdisciplines, including pattern recognition, machine learning. Okay, so that's it for chapter 1. I think we have about 4 minutes left. Let me just introduce a little bit of chapter 2. I'm not going to require you to do internet history. It's absolutely fascinating, but I'm not going to hold you responsible for that. Okay. Any questions with the introduction, chapter 1? No? Okay. So we've covered a lot of information, and this is to give you a very broad idea of the issues involved. And going forward, we will examine the various layers and all the issues associated with these layers in a so-called top-down approach. And so this is in contrast, this approach, to the bottom-up approach. And I like the top-down approach because you're starting with things that people know well, namely the applications. Okay, so we'll first talk about principles of network applications. And this is conceptual, and it introduces the idea of services, because every application provides a service. And when you write an application, it's important to know what the requirements are as far as the data is concerned in the messages that this application sends back and forth. Now, of course, there are different paradigms or ways that you organize your application. And if you think about what a network application does, you have pieces of software scattered around a network running on different machines, and they work together by exchanging messages to give you one complete application. Okay, so we'll also talk about protocols, very popular protocols. HTTP we'll focus a lot on. The other piece we'll focus a lot on is DNS, Domain Name Service, which is an important piece for mapping between human-readable domain names and machine meaningful IP addresses. Okay, so here are some apps, and you all are familiar with these apps and apps like this, so I won't belabor that. But when you create a network application, what is a network application? So imagine, you're going to go to a new city, and at first, until I actually needed to use it, I thought Google Street View was just dumb, right? Like, do all that, I don't care. I was going to another city, and I'd never been there. And so I looked up the city and said, oh, let me try this out. And you can do your virtual drive-through, and you can see like restaurants. Okay, I'm going to walk down here, get out the station there. I'm going to walk 3 blocks. I'm going to take a left. If I see the Panera Bread, I've gone too far. You can do that with Google Street View. And to you, it looks like one application, but really you have a bunch of servers involved, and they're interacting with one another, including your browser, to present the illusion as if it's a single application. Now, if you didn't know, you or one might think with a fast enough network connection, you think that everything's running in your browser on your machine, but it's not. Most of it is running on different instances of servers across the internet in various data centers, and each server is responsible for a certain piece of what you're seeing. And so when you create a network application, you write programs that run different pieces on different end systems or hosts. And they communicate with one another over a network, such as a web browser communicating with a web server. And you need to write software. You don't write, when you write the software for a network application, they only run on the end systems or hosts. None of this stuff runs on the routers and switches, the packet switches in the interior. And so we talked about these end systems or hosts, these machines on the so-called edge of the network, and they tap into the network through the access networks. We talked about these internet service providers, the global ones and the regional ones, which basically have a set of packet switches that are interconnected through a series of links at different speeds. Now, you don't have to deal with or care about what happens on the packet switches, right? All you care about is what happens on the end systems or hosts. And that's the beauty of it, how you keep this simple. All the complexity here is on the host. None of that complexity is on the packet switches, right? And so it's still important to understand the issues associated with the packet switches, but you don't have to care about them on your application specifically, but it's nice to know a little bit just so it'll help you write better applications. Okay, so we'll stop there, and it is now 12 after. We have 3 more minutes, so we'll end there, and we'll pick back up with this on Thursday. Look forward to your submissions.